In today's section, we're going to be talking about hypothesis testing. So when we were talking about inferential statistics in the last chapter, we mentioned that there's two types of inferential statistics. And what we talked about before, just as a reminder, this was estimation, where we took some value pertaining to a sample and a bunch of other samples and generalized that to a population. That was one type of inferential statistics, or statistics from a sample that help to infer ideas about the population. Now, there's another type of inferential statistics, and it's called hypothesis testing. And with hypothesis testing, this is where we will ultimately test some sort of hypothesis or compare these two hypotheses. And really, this is going to, in this class, regard a single population. In fact, for this whole section, we're just going to focus mainly on terminology. So we're not really going to be using the calculator in this section. It's not really going to come up. Really, we're just going to talk about terminology that'll help us view the next two sections. And so some of this terminology under this idea of hypothesis testing, well, to give an idea or to set the stage for hypothesis testing, this is a procedure used to test statements regarding a characteristic of one or more populations. So really, we're going to be looking at one population, but mainly what's important about this, the null hypothesis, which is denoted, it looks like H with a little zero next to it. You'll hear me commonly say H naught. That's a pretty general mathematical verbiage. So again, you'll hear me say H naught, but that's the null hypothesis. This is going to be considered a statement. The best way to I guess, characterize this, it's a statement that is assumed true until evidence indicates otherwise. It's assumed true. It's not absolutely true, but it's assumed to be true until some other alternative idea comes into play. And that segues straight into the alternative hypothesis, which is H with a little 1 next to it. So you'll hear me say H1. And it's a statement. So as you would imagine, it's some sort of alternative hypothesis to the null one. So it is a statement we are trying to find evidence to support. Now, a good analogy for all of this is if you think about a court proceeding, the defendant is normally given the benefit of the doubt. So the defendant is normally assumed to be innocent until evidence is proven, evidence proves otherwise. So the null hypothesis here would be that the defendant is assumed to be innocent. It doesn't mean they are innocent, so we are not claiming that they are innocent. They are assumed to be innocent. And the alternative hypothesis would be that they're guilty. That would be the contradictory or the different information that we want to provide to this to try and prove, possibly. So that's a good analogy to kind of understand what these two hypotheses represent. One of them is the assumption of truth, and then the other one is some alternative idea that we may want to support and try to see if that rejects the null hypothesis. And so we'll test this idea out for example 1 here. We'll determine the null and alternative hypothesis for a given situation. So it's something to do with a light bulb. The packaging on some light bulbs says that the bulb's going to last 500 hours under normal use. And then a consumer advocate would like to know if the mean lifetime is less than 500 hours. So the way we put all of this together, it's a pretty simple setup. So if anything, we need to know what variable we are dealing with. And really, the variable we are dealing with, they actually said it right here. We're dealing with the mean. So this is the parameter that we are dealing with, because in the very beginning, we said we test various hypotheses regarding a single population parameter. Our population parameter that we are testing here is the only one that shows up in this problem, the population mean. And remember that notation is it looks like a U, it's the Greek symbol mu. And so how we apply this, well, now this symbolism is going to help us construct two statements, one for the null hypothesis and one for the alternative hypothesis. And so here, I'm putting null and alternative just to help you all remember what these symbols correspond to. The null hypothesis is what's assumed to be true. It says that the bulb will last 500 hours. So that means it's saying that the mean is about 500 hours. That's it for the null. That's the assumption that's being made here. It doesn't mean that this is true. In fact, if it was true, then there's no point of providing an alternative hypothesis. It's assumed to be true, or it's given to be true. Now, what it goes on to say is, well, what's testing this idea? What is the person going against this idea trying to show? They would like to know if the mean lifetime is less than 500 hours. So for the alternative hypothesis, this would be that the population mean is less than 500, because they told us in words, the mean less than 500. And so that's it. That's really all we do here. That is the null and the alternative hypothesis. Just kind of establishing some of the terminology here. There's nothing really more to do for this problem. Does anyone have any questions before we move on? Okay, let's move on to testing, which is really not much of an extension from what we were talking about. It's just giving a way of giving some label to a situation we might have. So the situation we had above, it was an equal sign and a less than sign. And with that situation, we actually have a matching collection of symbolism. Now, that's just something to keep in mind, though. But this is giving us an idea about what sort of test or what sort of situation we are given here. It's just a way of labeling the situation we have. Oops. So with this, there's one of three situations that could happen. You can have a two-tailed test. We have, well, notice for all of these tests, no matter what, the null hypothesis has the same statement here. It's the same symbolism every single time. Parameter equal to value. They're all the same. So that part is consistent. So we're not going to focus on that as much. Notice how what changes is the alternative hypothesis. For a two-tailed test, we have a not equal symbol. For a left-tailed test, we have a less than symbol. In a right-tailed test, we have a greater than symbol. This is something that you would need to know. And one way to support this idea, so why does a not equal sign refer to two-tailed? Well, if we think about an inequality, or if we just think about a number line, if a value's not equal to A, then it's equal to stuff on the left of A and on the right of A. That's two sides. What about this one? If the parameter is less than some value, it's less than, then it's to the left, which is left-tailed test. Same thing with the right, but on the other side. Because here the inequality is a greater than symbol. So if you're greater than, then you're to the right. So this is another way you can think about some of these associations. So this, again, this just explains the situation that we have. So if we look above at example 1, we have an equal sign, which is always going to happen, and then a less than sign. Less than means that you have values to the left, which would be a left-tailed test. So if you want to come up here, you can identify that this is a left-tailed test. So again, it's just some association based off of the symbolism that we obtain in our hypotheses, in the statement of our hypotheses. And this is normally characterized by whatever inequality symbol you use for the null or the alternative hypothesis. We're going to do the same thing for example 2 here. We're going to state what the hypotheses are and determine if they're left, right, or two-tailed. So we'll start off with part 1 in example 2 here. There's some pharmaceutical company, and 2% of children experience headaches. A well, I guess I should say researcher, wishes to know if the percentage of children taking the new antibiotic who experience headaches is more than 2%. We need to take that whole paragraph and break that down into a statement, a nice compact statement for the null and for the alternative hypothesis. Now, one thing we need to ask is, in fact, I'm going to ask you all this. What population parameter is being tested here? Anyone want to give this a shot?
Children.
Well, parameter means mean, standard deviation, any of the population parameters.
Okay.
So it's not really a, it's a variable, not really antibiotic, children, side effects, company. It's not any of these nouns here.
Oh, you're asking it just like greater than or less than?
No, that's the inequality symbol. No, so here I just want the variable. So 2% is the quantity. 2% is the quantity. What's 2% as a parameter? What parameter is that? Where have we seen this? Came up in the last chapter. In fact, we had a whole section on just this parameter. Population blank. You know what an alliteration is? It is an alliteration with population. You want to know their English? It's an alliteration.
Sample distribution?
It's not that. Alliteration is a repetition of consonant. So population, proportion. It's a proportion. Population proportion. So 2% is the quantity. This is the population proportion. Oops. Population proportion, which tells us which symbol to use. That's P with the hat on top. So that's what I'm leading up to. You need to know what symbol to use. Is anyone in here an English major? Alliteration is a repetition of consonants. What's the one for vowels? Can't remember. Oh well, we'll look it up later. Okay, so population proportion. So now we know what symbol to use. Something to do with this symbol. So now we need to figure out, well, what's the assumed hypothesis here? Well, that's where the quantity comes into play. It's assumed that 2%, well, actually, I'll use the decimal. So instead of using 2%, I'm going to convert that to a decimal. It's assumed that 2% of children taking competing antibiotics experience headaches. Now, what's the alternative? A researcher, so technically, yeah, that should say researcher, wishes to know if the percentage of children taking this is more than 2%. More than is a greater than symbol, and 2% is just 0.02. So those are the hypotheses. And now we need to figure out which tail this is. So I'll do this. All right. What tail test is this? It's a right. And if you scroll up, in fact, I could fit it on the screen here. The symbols for the right tail test perfectly correspond to our symbols. There's an equal to sign and a greater than sign. Additionally, if you're greater than some value, then you're to the right of that value. That's another way you could think about the direction of the tail. So that's already part one right there. Part two, they tell us that the standard deviation is for a 64-ounce bottle is 0.23 ounces. And they want to know if there's variability different than 0.23 ounces. So let's try this again. See if everybody can redeem themselves this time. What's the parameter here? It's standard deviation. This one's easier because, yeah, of course, they say standard deviation. So if anything, we have the population standard deviation. And in this section, we assume that everything is population because hypothesis testing deals with population or parameters, which associate with populations. So this is population standard deviation. And the symbol for that, sigma, lowercase sigma. So now we have a symbol to work with. Okay, so if anything, well, I guess let me ask you all, what's the null hypothesis here?
Two-tailed test.
What's that?
A two-tailed test?
I mean, you gave me the last question I'm going to ask. So we're going to come back to that. What's the null hypothesis as a statement?
Equal to 0.23 ounces.
Yeah, that's it. Equal to 0.23 ounces. That is exactly it. So then what's H1? Or the alternative hypothesis?
Not equal.
Yeah, it's not equal. Yeah, so notice they don't say less than, more than. They just say has variability different than, which they try to throw you off. As in, it could be greater than, it could be less than. But because they have an equal sign and then a not equal sign, when you try to figure out what tailed test you have, that's a two-tailed test. Because there's an equal sign, a not equal sign. So that's it. It's a two-tailed test. That's pretty much a third of the homework right there is just making those observations. Does anyone have any questions before we move on? Okay, so there's different outcomes from hypothesis testing. So now we've been talking about how to set up hypotheses, but what about situations pertaining to outcomes from this? And so there's 4 different outcomes, and it seems technical at first, but it's really, I think it's more so intuitive than you think. So with these hypotheses, remember the goal is you're assuming that the null is true, and you want to see if you could prove the alternative or not. Or in other words, reject the null to support the alternative. So there's 4 different things that could happen. You end up rejecting the null when the alternative is true, which means you did what you needed to correctly. Now, I'm going to tie this in because this seems technical at first. I want to tie this in with the analogy I used earlier about a court proceeding. So let's say null represents innocent person, alternative represents guilty. So reject innocence when guilty is true. Now, what you did is you successfully convicted a guilty person. That means you made a correct call. All right, you can do that. Do not reject the null hypothesis when the null hypothesis is true. So let's switch out the word null with innocent. Do not reject innocence when innocence is true. So basically, in other words, an innocent person is found innocent, which is also good. You don't want to, convict someone who's innocent, obviously. So you can either successfully convict a guilty person or successfully find an innocent person innocent. Now, those are the 2 best case scenarios, but you can make errors because you don't know, at the end of the day, you don't necessarily know what may be true or may not be true. I mean, it happens in court cases all the time. Innocent person's found guilty, guilty person's found innocent. Now, a type 1 and a type 2 error are ways of looking at this. So a type 1 error is when you reject the null hypothesis accidentally, but the null hypothesis ends up being true. So again, let's switch out the word null with innocent. Reject innocence when innocence was actually true. So this would be falsely convicting somebody. That's how this analogy works. You would falsely convict an innocent person. That's a type 1 error. A type 2 error would be the opposite. Do not reject the null hypothesis when the alternative hypothesis is true. So a type 2 error would be, well, if we switch out null and alternative with innocent and guilty, do not reject innocence when guilty is true. So you found a guilty person innocent. That would be a type 2 error. So these are the 4 different outcomes. So they're a little bit more intuitive. It explains the different situations that may occur. But so that's something to keep in mind. That'll show up in, I think, the remainder of these problems here. Type 1, type 2 errors if they do occur. So let's look at example 3 and kind of see this situation play out a little bit more. You might recognize example 3. We actually already did it in example 1. It's the light bulb problem. So I'm going to go ahead and state the hypotheses again that we already found. It's equal to 500. It was less than 500. Again, we did this in example 1. Now, what they want us to do for part B, so I'll put down the 4 answer choices as very similar to your homework. So we need to select the one that is a type 1 error. A type 1 error. So what that means, a type 1 error, I'll try to keep a type 1 error definition on the screen here as we look through this. You reject the null hypothesis when the null hypothesis is true. So all it's doing is talking about, notice it's saying null hypothesis everywhere. It doesn't say anything about alternative. So we should be looking solely at this statement. So as I look through all of these, the first one is automatically wrong in part B. The reason why? It says less than. It doesn't even, well, type 1 errors do not look at the alternative at all. So the first one's wrong. Well, the last one is definitely wrong as well, because it's talking about greater than. Again, there's no need to even go to that symbolism. Back to my notes, I should have put less than, but same idea. So just by using that alone, we're down to 2. We should not be talking anything about less than or greater than. Type 1 errors only pertain to the null hypothesis. Now let's see, the wording changes here between these two leftover options: rejects or fails to reject. Well,
What would be fails to reject?
well, look what I just circled. This is reject. So here we will be rejecting. Because notice rejects and rejects. And notice what you said makes more sense for a type 2 error when you do not reject or you fail to reject. So it's got to be the second one, using that sort of terminology there. So notice what the answer choice we selected says. You reject the hypothesis that the mean lifetime is 500 hours. So the mean lifetime is 500 hours. That is the null hypothesis. That's exactly what the null hypothesis says. Mean is 500. That's exactly what it says in words. So what this says, it rejects the hypothesis that the mean lifetime is 500 hours when it is the true mean lifetime. So this is if you accidentally disprove or you accidentally reject something that's true. That is an error. And in particular, that's called a type 1 error. So that's how someone could commit a type 1 error. So we have a type 2 error as well. Notice it's the same answer choices. Now, a type 2 error does involve both the null and the alternative hypotheses. There we go. Hypotheses. So we can't use what we used before, because with the type 2 error, we have a null hypothesis and an alternative hypothesis. So the terminology can still, we can have, inequality symbols. So one thing that I think would be helpful to utilize is that it says do not reject. And with the phrasing do not reject, that means fails to reject. We can instantly get rid of the first two. We can instantly get rid of the first two because they both say reject. But for a type 2 error, our phrasing is do not reject or failed to reject. So we need to utilize this phrasing fails to reject. Now, it seems like the initial statement, everything before the comma, is true, or at least symmetric in both cases. But it's the really the predicate or the following statement when everything changes. When it is the true mean lifetime, or when the true mean is greater than 500 hours. Now we know from And again, like I said before, greater than should say less than in both problems. Should say less than. If you have the notes typed out, they should say less than. Now, it says the null hypothesis should be stated first, and then in the following statement, the alternative hypothesis should be stated. The alternative hypothesis is less than 500, and we see that the last one actually does state less than 500. The third one doesn't say anything about less than at all, so it doesn't even acknowledge the alternative hypothesis. Our statement needs to acknowledge the alternative hypothesis because a type 2 error does that. So it has to be the last one. Does anyone have any questions before we move on to the next example? Okay, so let's move on to example 4 here. State the conclusion based off of the results of the test. So there's students who earn a bachelor's degree within 6 years. The president of a university believes that the proportion of students who enroll have a higher completion rate. The null hypothesis is rejected. Now, really what it's asking for us to do here, so you don't need to state the hypotheses here. It's not necessarily asking for the hypotheses themselves. It's asking for, well, I guess I'll state them anyways. It does help in the conclusion of the problem. So I'll go ahead and state them. They do tell us the population parameter. It's the proportion. Means p hat. So the null hypothesis, they assume that the proportion who earn a bachelor's degree within 6 years is 0.399. President of a university believes that this is actually higher than 0.399. So that's why I have a greater than sign. President believes that it's higher than. So these are the hypotheses. And then they tell us that the null hypothesis is rejected, which means that, well, it means that they determine that the proportion is not, in fact, 0.399. They rejected that null hypothesis. And they want to know what the conclusion would be based off of rejecting the null hypothesis. Now, I think the wording that your homework uses, there is sufficient evidence to support that. So we rejected that the proportion is 0.399. So if you reject the null hypothesis, and that means you can assume validity in the alternative hypothesis. So support that the proportion is greater than 0.399. So basically, whenever you reject a null hypothesis, then the alternative hypothesis can be stated. Simple as that. Or in other words, now of course, there may be errors involved, but this problem isn't really asking us to look for errors to really go into the depth of this problem. So this would be the equivalent. If you reject the null hypothesis, this means if you find that someone is not innocent, if you replace the word null with innocent, you reject the notion that they are innocent, then guess what? They are guilty. So there's sufficient evidence to support that they would be guilty. You want to think about it as that analogy. Let's look at the second one. So the time to order and deliver a pizza is 48 minutes, and there's a new system to reduce the time. Well, the first question is, what's our proportion? Proportion is the mean. Definitely can't, or the parameter, I'm sorry, the parameter is the mean. Definitely cannot be a proportion because there's no percentage, there's no ratio, and it's not standard deviation, it's the mean, the population mean. The assumed mean is 48 minutes, and the alternative is to reduce the time, so less than 48. And then they say the null hypothesis is not rejected. So then the question is, would there be sufficient evidence to then say that the mean time is 48 minutes? Seems kind of tricky. The answer is there is not sufficient evidence. There's not sufficient evidence. Normally, you assume, so again, going back to the court analogy, you assume that a person's innocent, but you're not saying that they are innocent. You assume that they're innocent. And if you find them, and really what this is saying is, if they're not guilty, then this is a lack of showing that they're guilty. It's not, you're not proving that they're not guilty. It's more into philosophical stuff. You're not proving that they're not guilty. You fail to prove that they are guilty. And so it's not, so it's still insufficient to say that they're innocent, but really they're just not guilty according to all this other stuff. I don't know court too well. I think it is a good analogy still, but this is to kind of lasso this in a more refined nature. There is not sufficient evidence to support that the mean, since we have the mean now instead of the proportion, is 48. And we don't have to use an inequality symbol because it's referring to the null hypothesis now. Because we did not reject the null hypothesis, so it's still something to consider. So this is these are generalities that just correspond to if you reject the null hypothesis versus if you don't reject it. The hypotheses themselves do not influence this problem at all. It's just conceptualization of you reject a null hypothesis, no matter what the situation is, then you can adequately say, then we can accept the alternative hypothesis. But if you don't reject the null hypothesis, it doesn't mean that it's inherently true. It just means that it's, well, I don't want to use the word vacuously true. That's more of a philosophical term, but it just means that you might have to do more tests or something. But assumption of truth doesn't mean absolute truth. Again, that's more philosophical than anything. Okay. Let's, well, there's a quick definition here. The level of significance, if you see this variable alpha in this chapter, so in the last chapter, it talked about the level of confidence. This one, it talks about the level of significance. It's the probability of making a type 1 error. So this is rejecting a null hypothesis when you shouldn't have. It's the probability of doing that. But, well, I guess from there, let's talk about marijuana. So example 5, there is a study. So I looked the study up, and according to this study, 31% of college students reported using marijuana. I'm really surprised it's not more, but some political pundits hypothesize that this number is going to go up when recreational marijuana is legalized in a certain state. So let's kind of talk about this study a little bit. So let's first determine the null and the alternative hypotheses here. We need a symbol to work with first. So what's the parameter in this problem?
Portion?
It's proportion, because there's a percentage. 31% is the quantity. That quantity is a proportion. So we can go ahead and figure out right fast the hypotheses here. So we already know the quantity. I'm going to go ahead and fill in that one. And pundits hypothesize that this will increase. So that's the alternative here. So this would be the null and alternative hypotheses that would be used to test the causality, or the cause and effect, or really just the cause of this legislature. So assume in part B that they actually show, well, the wording here is a little technical, provides enough evidence to conclude this causality. Causality means cause. What's the cause here? Well, ultimately, this cause of whenever you legalize recreational marijuana, the percentage of people who smoke it does in fact increase. Assume that's what they found in their study. So the percentage of college students who reported using marijuana increased. Assume that is true. So it's assuming that the alternative is true, which means you are rejecting the null. So so that whole sentence can be wrapped up as reject the null, because you proved that the political pundits were correct. So assume that they were in fact correct, which means their alternative hypothesis was in fact true. So then you could say there is sufficient evidence. So this is what we just did in the last problem, actually. There is sufficient evidence to support that marijuana usage will increase. Again, this is based solely off of whether we reject the null hypothesis or don't reject the null hypothesis. Now, suppose something else happened instead, a parallel universe where they did the study and they found that, let's set up a stage a little bit. Let's say after 5 years after weed's been, its recreational usage has been legalized, the percentage stayed the absolute same. There was no increase or decrease in the percentage of college students that reported using it. So that means the pundits made an incorrect statement. They thought that the percentage would increase and nothing happened. They committed an error. What kind of error did they commit? Is it a type 1 or a type 2? Type 1 is when you reject the null when the null was true. And the second one is, I'm trying to remember all these. You don't reject the null in the what's the second one? I always forget that one. Yeah, you do not reject the null when the alternative is true. So what the pundits did They thought that the null hypothesis was wrong, and they were in fact wrong. This all pertains to a type 1 error. Because they thought that the percentage staying at 31% was wrong, but it ended up being true. So they rejected the null hypothesis, but the null hypothesis ended up being true after all. So if this hypothesis was tested at the alpha is equal to 0.05 level of significance, this is a really easy part. It just tells you that the probability is 0.05. There's not really much to do with level of significance in this section, but they brought it up in this section, so I figured I would as well. So notice 0.05 is just telling you how to interpret that symbolism. Does anyone have any questions about this? Would you all like to get out early? Okay, cool. Get out. If you have any questions about the quiz, I'll stick around. Remember, there's a quiz due tonight. Don't forget the quiz. If you have any questions about it, I'll stick around. Other than that, get out early. Go enjoy the sun. Have a good day.